So we can continue with this fourth part, where now we'll see, so we started in the second part, just denoising. We've seen that there's many different ways of doing self-supervised learning for denoising. Then we saw with Mike in the third part how to deal with incomplete operators when we have a reconstruction problem and there's some missing information. And we saw that we required multiple operators to solve the problem. We required kind of different cameras serving the same distribution of images for solving the problem. And what I will do right now is to say what happens now if we have a single operator. So we have a single camera that observes a lot of different measurements, but it's always the same operator. And one more time, and this is the third and the last one, if you don't do, if you don't impose any other information or any other prior that you have about the problem, there is infinitely many bad solutions, because the neural network can learn anything in a null space of the operator. So what can we do if we don't have multiple operators, which is the setup of most of practical imaging settings? We can leverage some prior information, and this prior information will be relatively mild. The idea is that the distribution of images is generally invariant to a group of transformations. Okay? We think about the distribution of natural images, say cats here. In a distribution of cats, we'll have a cat more to the right, to the left, and so we can write this mathematically as having a group of transformations. So this is the action, a linear action of the group of transformations, which is basically a bunch of invertible matrices in Rn times n. And what we say is that for every signal x in our set x, in the set of images, when we apply a transformation, we land in the same set. Okay. So be careful here. I'm not speaking about invariance of the specific image. I'm not saying the image, the cat image itself is invariant. It's the distribution that it's invariant. And this can be done for translations, but there are many other invariants, the symmetries that we can use, like rotations, permutations, amplitude invariance, depending on the specific data we have at hand. And so here comes the trick. The idea is to say we write our inverse problem here, y equals ax. So I remove the noise to make things easier, but the noise will come back later. And I can just write a transform, let's say a shift, and its inverse. So I have not changed the original equation at all. But now looking back at it, I see that I'm actually observing another image, x prime, the shifted version of x, to another operator, A composed with TG. So assuming this invariance, it's kind of implicitly giving us access to more operators, which are the transform version of the original operator we have. So, so now, even though in practice we only have one operator, implicitly it's as if we had now G different cameras, one per every transformation in our set of transformations. And the key here will be that maybe these different operators, so A composed with TG, might have a different null space, and so they might give us information about other parts of the space. So if you think about in painting and we use translations, the mask will be moving around, and so the missing pixels will change. And now that we have multiple operators, everything that Mike spoke in the previous parts holds again. Okay, but now we're just using invariance. So we can kind of rewrite some of the necessary conditions, but now with invariance. So if we can write the ensemble of AG matrices now at A composed with TG, and we need that this, when taking into account all the possible transformations of our matrix A, we get something that is full rank. We think again intuitively about imaging painting. We have a certain fixed mask A1, and then when we consider all the transformations, we'll get its translated versions, and when we sum over them, we should cover the whole space. We shouldn't have any hole. If we do some linear representation theorem, we can get some bound on the number of measurements per operator that we need. So which basically is n over the number of group of elements in the group. So the larger the symmetry, the larger of transforms there will be, the more implicit operators I will have, and the more chances we have that this thing will have full rank. Okay. So now one thing that we learn of this kind of a corollary, but it's a very important corollary, is that we need that the operators are not so equivariant, and I will move my video so we can see this. Are not equivariant. What do I mean by that? To remove action. Because if they're equivariant, it means that the TG matrices of the transforms commute with the operator A. And if they commute, it's very, very easy to show that this matrix summing over all the transforms will have the same rank as the original matrix A, which has a rank that is smaller by definition to the rank n of the whole space. Okay, so if the operator is equivariant to the action, we will not get additional information. The null space of the problem will not change. So this kind of raises the equivariance quiz I have here. Back again. So we can think now of which operator will be useful for which inverse problem. And we have here a list of different common inverse problems that we find in practice and common transformations that we can assume that our distribution of images is invariant. So if we think about translations, which of these operators will be equivariant to translations? Well, the answer is all of them except in painting, if the mask is specific in a certain part of the space, because the rest of the operators are diagonalizable in Fourier. They are or translation equivariant. So in the translation will only be useful in this specific case for giving us more information. What about rotations? So now we have less operators are equivalent to rotations. The ones are convolutions with isotropic filters like Gaussian blur will be equivalent to rotations, but the rest are not. For scalings, so zooming in and zooming out, we'll only have approximate equivariance by a CT operator due to the Fourier slice theorem. And amplitude, so changes in amplitude of the signal of the contrast of the image, all of them will be equivariant because they are linear. So all linear operators are equivariant to in amplitude. And now we know that this invariance can be useful for having more information about the problem. And the question is, how can we enforce it in practice in our imaging system? And here, the key observation is that what we need is equivariance of the whole imaging chain. What do I mean by that? I mean that if a cat moves in the real world, and we take an image of it, and we reconstruct the image that we reconstruct should move equally. So we should have equivariance from this first stage to the last one. Which does not mean that we need equivariance only on the reconstruction F. One would be tempted to say, I will use a CNN. A CNN is shift equivariant, but having an F that is equivariant does not guarantee that A composed with F will be equivariant. Okay. So how can we then impose that that our imaging system F composed with A is equivariant? Well, one solution is to do it via training, and we'll end up with the idea of the equivariant imaging loss, which basically says reconstruct something. So we get x hat here is not the ground truth, is whatever was reconstructed by the neural network. We will generate a new measurement. So we will transform that image, generate a new measurement, and reconstruct it again. And we want that whole thing is 0. So the system is equivariant, right? And under some strong assumptions on the distribution, that the imaging set, the signal set, sorry, is linear, and we have a measurement consistent reconstruction, we can show that this loss actually is an unbiased estimator of the supervised case. So the idea is that this averaging over the group is giving us information in the null space, and that we are able to learn that information. So now we end up with the idea of equivariant imaging, or the robust equivariant imaging, where we have two terms as in multi-operator loss. The first term will enforce equivariance of the imaging system, and the other loss will enforce measurement consistency. If we have noise, we will use something like sure or any of the losses that we saw in the second part. Or if we don't have any noise, just plain measurement. So yes, here we are not limited to sure. You can use measurement splitting or so let's look at some results. So now, differently from the previous part where we had multiple masks, here we have a data set of MRI measurements, all of them observed with the exact same mask. Okay, so we don't have, a priori, we don't have any information in the null space, so in the missing frequencies here. So if we do something naive, which is training a neural network on measurement consistency alone, it will learn something very close to the pseudo-inverse, because it doesn't have any information in missing frequencies. Okay. But if we now assume that this distribution of knees is approximately rotation invariant, because you can rotate the knee and there will be another valid knee in the data set, it's as if you were rotating the mask, the Fourier mask, because the rotation in pixel space is a rotation in Fourier space. So when we rotate the mask, you see that we're covering the whole space. And when we then use the equivariant imaging loss, we can obtain something that is very close to the supervised learning case without any ground truth. Here, assuming invariant rotations. Something important to remember here is that not every transform would be useful. If we use translations or shifts, we would not get more information, because this is equivariant to shifts, in the sense that a shift of the image space is just a multiplication by a complex exponential in Fourier space, so it's not moving the mask around, not giving us more information. But the rotation is. Another intuitive way of thinking about it is that the artifacts related to the missing information here have some direction. So when we rotate our reconstruction, this direction will get removed. Whereas they are translation, the artifacts are translation invariant. Another example is CT. So in sparse CT, we observe just a few views of the image here. I think it's of a chest. And here we'll add some Poisson Gaussian noise and use a Shor type loss to handle the noisy part. But again, we can use equivariant imaging with equivariance to rotations to learn something that is very close to the supervised case, while only having observations of CT observations always in the same angles. And while rotations, well, the intuitive way to think about is that we are kind of rotating the CT machine, so the angles that we're obtaining, our projections are changing with the rotations. We're getting more information and we're covering the whole space. We can also do this for learning in from measurements that have lost high frequencies. So here, rotations and translations will not work. For example, if we have lost information via some isotropic blur operation, because this is both translation and rotation equivariant. But we can use this scale, so invariance to zooming. If we assume that our distribution of images is somehow fractal, we can zoom in and we'll get another valid image. We can exploit this information to obtain features that were not observed in the blurry.
A question about this specific example.